said it was a lot.
Yeah, a lot that we're supposed to do today. It don't have to be, that's what I'm trying to tell you. But the more we do today, the less we do tomorrow.
Can't you just like divide it equally?
I'm old. Sorry, y'all. All right, 8.2, estimating a population proportion. And again, it's supposed to be a lot today and only like 2 pages tomorrow. I'm gonna try to even it out a little bit. So I may have to adjust your homework. But again, the more we do today, the less we have tomorrow to do. Okay, so I would rather not do anything on a Friday than not do anything halfway on a Thursday and halfway on a Friday, if that makes sense. So work a little harder today to relax a little bit more tomorrow. All right, in section 1, 8.1, we saw that a confidence interval can be used to estimate an unknown population parameter. We are often interested in estimating the proportion P of some outcome in the population. This section shows you how to construct and interpret a confidence interval for a population proportion. So we're supposed to do an activity with beads. Again, we're not doing those because happy COVID. So you guys can go look at that if you want to, but everything that they do in that activity is explained within the notes. So conditions for estimating P, you need to know the conditions that need to be met. Before constructing a confidence interval for P, you should check some important conditions. The first condition is that it's random. The data should come from a well-designed random sample or randomized experiment. Otherwise, there's no scope for inference to a population or inference about a cause. Okay, so we don't want a voluntary response. We don't want, because those cause too much bias. So we're not going to have any inference on that stuff. So we want a really good like SRS. So if we can't draw conclusions beyond the data at hand, there's not much point in constructing a confidence interval. Another important reason for random selection or random assignment is to introduce chance into the data production process. We can model chance behavior with a probability distribution like sampling distributions of chapter 7. The probability distribution helps us to calculate a confidence interval. All right, you got to check the 10% rule. We already know what the 10% rule does. So the procedure for calculating confidence intervals assumes that individual observations are independent. Well-conducted studies that use random sampling or random assignment can help ensure independent observations. So like when we were doing bins, We're not doing bins because we're not worried about binary. The first thing we're worried about this time is random, and then we're going to check our independent. And remember when we didn't know if it was independent because we weren't replacing our population. So when you take an SRS, you are not replacing. So you're changing that chance. You have to take that 10% or you have to check that 10% rule. So, however, our formula for the standard deviation of the sampling distribution of p hat, which we know from last unit, is the square root of p 1 minus p over n, acts as if we are sampling with replacement from a population. That's rarely the case. So what I just told you, if we take an SRS, we are not putting people back into that population. We're taking them out and changing that chance number. So this assumes that we're putting them back. So we got to check that 10% rule to make sure that we're okay with that. So that's rarely the case when sampling without replacement from a finite population. Be sure to check that n is less than or equal to 1/10 of n. That's that 10% rule. So 10 times n has to be less than the population. This should say sampling more than 10% of the population would give a more precise estimate of the parameter p, but would require us to use a different formula to calculate the standard deviation. And that's of the sampling distribution. And then the last thing you need to check. So random, 10%. Again, what is random? Making sure we have what? What'd I tell you?
No.
What does it want when it's asking for random? A random what? So an SRS, it'll literally say took a random sample or a simple random sample. Okay, so we want it to be random. What's 10%? Yeah, and why is because we want to make sure that they are independent. Okay, they don't because we don't replace it. So if you're taking an SRS of people, you're not replacing. That is not independent. So you got to do the 10% rule to override that missing independence. Okay. The last thing that you're going to do is large counts. All of these you already know. They're just conditions for making this interval. So the method that we use to construct a confidence interval for P depends on the fact that the sampling distribution of P hat is approximately normal. So we need it to be normal. Last unit, how do we check if it's normal? We use large counts. Okay, same thing you've been doing. From what we learned in chapter 7, we use the normal approximation for the sampling distribution of P hat. As long as NP is greater than or equal to 10 and N1 minus P is greater than or equal to 10. They are the same conditions we have always checked. So here's your conditions in a box. These are the ones you're going to have to check. Okay. Random is that the data comes from a well-designed random sample or randomized experiment. It will tell you. We took an SRS. We took a random sample of people. People were randomly selected. Okay. Then the 10%, when sampling without replacement, check that N is less than or equal to 1/10 N. Again, that's the 10% rule where you did N times 10 and then check to see if that population was bigger than that. And then large counts, both N times P hat and 1 minus P hat times N are at least 10. All this that I skipped is just talking about the large counts and stuff we already know. So I just skipped it. You already know it. If you want to fill it in, that's fine later. I'm not worried about it. When Mr. V's class did the beads activity, and I told you about that a minute ago, you can go back and look at it. It's not important. They got 107 red beads and 144 white beads. their point estimate for the unknown proportion P of red beads in the population is this. Remember, their point estimate is going to be the proportion. To find our proportion, it's what we want over our total. Nope. Nope. P is your population proportion. That's what we don't know. We can find P hat. We're using P hat to determine P. Okay, so remember our interval is, you know, when we write it out or whatever, it contains the true proportion of context of the problem. So we use P hat to find that interval, which should contain this P. So we're using the interval to find this. And that's all it's saying. We don't know our population proportion, so we're going to use our sample proportion to figure it out. That's all we're doing, okay? So we wanted red beads in this situation, and I know that's not on here, but here's where it talks about the proportion of red beads. There was only red and white in there, so when you add those up to get your total, you get 251, which gives you a proportion of 0.426. So let's see how the conditions play out for Mr. V's class. So we're going to the next page. This is really quick. We're just checking conditions. Okay. Mr. V's class wants to construct a confidence interval for the true population proportion P of red beads in the container. Recall that the class's sample had 107 red beads and 144 white beads. Check that the conditions for constructing a confidence interval P are met. So the first one we need to check is it's random. Does it tell us that it's random? In this one, does it tell us? No. In the actual thing, it says the class took a random sample. Okay, so if we go, let me look at another example and I'll show you. Right here. So number 2 on this one, it says a quality control inspector takes a random sample. Right there, problem states that it's a random sample. Got it? This one, if you're looking at it, does it take a random sample? You see what I'm saying? So you'll know. What is this one? Convenience, because it's the first 100. Okay, we'll get to that in a minute. So this one is, and again, that's within the activity, so don't worry, it will be within the problem. So the class took an SRS of 251 beads. You want to check your 10% rule? What was your N? What was your sample size? 251. So we do N times 10, or 251 times 10. And in the problem, again, because I didn't read it to you, I'll let you know when you go back and read it if you want to. Mr. V said there were 3,000 beads. So are we okay? Yes. So the 10% is fine. That is less than the population. The last one we need to do is large counts. So the first thing that we're going to do is N times P hat. N was 251. P hat we found on the other page, 107 over 251. If you can multiply quickly in your head, these two will cancel out and you just get 107. Is that greater than or equal to 10? Yes. The proportion that were not read was 144 out of 251. Again, doing quick math, your 251s will cancel out, leaving you with 144, which is greater than or equal to 10. So this is what this means. All conditions are met. You will be doing this on Albert at some point. There are a lot of questions on there that ask if they can construct a confidence interval, and this is exactly what you're going to follow. All conditions are met. So it should be safe to construct a confidence interval. So when we talked about that n p hat and n times 1 minus p hat, notice how the 251s canceled out. That will happen every time that there's a proportion. So notice that n p hat and n 1 minus p hat should be whole numbers. You don't really need to calculate these values since they are just the number of successes and failures. So it's those top numbers, what we wanted and what we didn't want. In the previous example, we could address the large counts condition by saying the numbers of successes 107 and failures 144 in the sample are both at least 10. Does not matter which way you do it. I do not care. I keep it consistent, so I just go ahead and multiply it. Okay, it's up to you though. All right. What happens if one of the conditions are violated? So if the data come from a convenience sample, or a poorly designed experiment, there's no point conducting a confidence interval for P. Violation of the random condition severely limits our ability to make any inference beyond the data at hand. The figure below shows a screenshot from the confidence intervals applet. I told you about it. We didn't do it. We set n equal to 20 and our proportion to 0.25. The large counts condition is not met because NP equals 5. We use the applet to generate 1,000 95% confidence intervals for P. And only 902 of those 1,000 intervals contained that proportion 0.25, which is a capture rate of 90.2%. When the large counts condition is violated, the capture rate will be lower than the one advertised by the confidence level. Okay, make sure you know that. The capture rate will be lower than the one advertised if large counts is violated. So if it's not random, we can't make any kind of inference on the data or on the population. If the large counts is violated, the capture rate will be lower. And then that just leaves the 10% condition when sampling without replacement from a finite population. Large random samples give more precise estimates than small ones. We know that. Why? The larger the sample, what? Less variability. So randomly selecting more than 10% of a population should be a good thing. Unfortunately, the formula for the standard deviation of P hat that we developed in chapter 7 P 1 minus P over N, take the square root, is not correct when the 10% condition is violated. The formula gives a value, should say a value, or just gives values that are too large. Confidence intervals, this is important, based on this formula are longer than they need to be. If many 95% confidence intervals for a population proportion are constructed in this way, more than 95% of them will capture P. Okay, so if large counts is violated, less will be captured than the actual 95%. If 10% is violated, more will be captured than the 95%. So the actual capture rate is greater than the reported confidence level when the 10% condition is violated. So remember that. All right, so on the next one, each of the following settings, we're just going to check conditions. Okay. So the first one, we need to check if it's random. And what did you guys say? It's not, because it is a what? So that one is not met. We're still going to go through the rest of them. 10%. How would we check 10%? Ten times 100, which is? Okay, when it says a large high school, it's thousands and thousands of students. Y'all understand what I'm saying? A large high school. We are not a large high school, and we're almost at a, I mean, we got like 700 and some students. Y'all see what I'm saying? So double that for like North Davidson. All right. So it is good. It is less than 10% of the population. Okay. And then we check large counts. And remember, when we're working with proportions, you only have to do successes and failures. You don't have to actually find the proportion and then multiply it by. So it says they asked the first 100 students to arrive at school one morning whether or not they slept at least 8 hours the night before. Only 17 say yes. So what is our number of successes? 17. Which is greater than or equal to 10. What would be our failures? Say what? Which is how many? Great job, math students. 83. You are correct. You are correct. It's everybody else. And that is greater than or equal to 10. So that is perfect. It is met. All right, check the second one. A quality control inspector takes a random sample of 25 bags of potato chips from the thousands of bags filled in an hour. Of the bags selected, 3 had too much salt. So is it random? Why? It said an SRS or randomly selected bags. Once we get into this more, you can just say stated within the problem. Doesn't matter how you write it. Either stated or write out what they said. 10%, how do we check it? Do you think 250, the population is greater than 250? Yes. Pretty sure they make more than 250 bags of potato chips. Okay. Large counts. Remember, you do successes and failures. So there's 25 total bags. What was your success? It doesn't matter. You don't have to label them. So 3 and 22 are your 2 numbers. 3 is not greater than or equal to 10. So it fails large counts. What does that mean? But what happens when we have a violation of the large counts and we try to take a confidence interval? Flip it back over. The capture rate will be lower than the actual confidence level. Good job. All right, everybody go to that. It's pretty simple. Constructing a confidence interval for P. This is where it gets crazy. You ready? When the conditions are met, the sampling distribution of P hat will be approximately normal. Why are they normal? Because it passed the large counts. With a mean of P, just like we did before. So there's nothing new there. And then your standard deviation. Why do we use this formula? The P1 minus P. Yeah, because we have a proportion. That was not like a trick me question. It's because we have P. What if we don't have P? What else will we have? What's our other formula for standard deviation that we learned? If they provide the population standard deviation divided by the square root of n. Okay, so there may be two. But we're only working with proportion, so this is the only one you got to worry about now. Okay. The figure below displays the distribution. Inference about a population proportion P is based on the sampling distribution of P hat. So again, P talks about the population and P hat talks about the sample. We can use the general formula from section 8.1 to construct a confidence interval for an unknown population proportion P. So remember that formula was statistic plus or minus critical value times the standard deviation. And remember that was the standard deviation of the statistic. Okay. The sample proportion P hat is the statistic that we use to estimate P. Doing so makes sense if the data come from a well-designed random sample or a randomized experiment. So again, the random condition is met. The standard deviation of the sampling distribution of P hat is that same formula we've been writing. But we can only take that if the 10% condition is met. Because we don't know the value of P, we replace the sample proportion with P hat. The resulting quantity is called the standard error. For the sample proportion P hat. All of these formulas are on your formula sheets. Your formula sheets are linked into your Canvas if you ever need them. Okay, they're always there. Your tables, everything is always there. So you don't necessarily have to have your book. You can just look it up. All right, so standard error of P hat is the same formula. All they did was interchange to P hat. It describes how close the sample proportion P hat will typically be to the population proportion P in repeated SRSs of size n. And this is just a normal curve. It doesn't, there's not really anything to it right now. Okay. So what is standard error again? It's when the standard deviation of a statistic is estimated from data. The result is called the standard error of the statistic. All right. So in our formula, we know how to get our statistic. That's our p-hat. Okay, what we want over our total, or if they give us the actual proportion, it's the actual proportion. Everybody okay with that part? We're moving on. Plus or minus the critical value. So how do we get the critical value for our confidence interval? If the large counts condition is met, we can use a normal curve. For the approximate 95% confidence intervals of section 8.1, we used a critical value of 2. Based on the 68, 95, 99.7 rule for normal distributions. Okay, remember 95% of the data is within 2 standard deviations of the mean. We can get a more precise critical value from table A or a calculator. As the figure below shows, the central 95% of the standard normal distribution is marked off by 2 points. I'm going to pop this down here for a second so you guys can see. Those 2 points are on either end of the normal curve. One is negative Z star, one is positive because this one's below the mean, this one's above. But regardless, the Z star, and that's what you call it, Z star, is 1.96. Negative Z star is negative 1.96. We use the star to remind you that this is a critical value and not a standardized score that had been calculated from data. So it's not the Z stuff that you guys did on your pre-response. All right. To find a level C confidence interval, we need to catch the central C percent under the standard normal curve. Here's an example that shows how to get the critical value Z star. For a different confidence level. We can either use table A or we can use technology to find the critical value Z star for 80% confidence interval. Assume that the large counts condition is met. Why do we assume that it's met? What's the purpose of the large counts? We've done this for like 2 chapters now. Why do we do large counts? Yep, that's 10% rule. What do we do after large counts? Like last unit, what do we do after large counts? We did what? No, that was after 10% rule. Two chapters now and you don't know what we do. That's a problem, okay? Y'all have got to start remembering this stuff. Not mad now, but you're gonna have to do it this chapter again and again and again. So 10% rule is when we fail the independence, okay? So we're not replacing, we have to check the 10% rule. If we replace cards in the deck, so draw one and put it back in, we don't have to check 10% because we are replacing. So that didn't change anything, it is independent. But when we take random samples, if I take a sample of the classroom, I'm not putting you back in. So we have to check the 10% to make sure it's okay. After that, we take the standard deviation. After that, we do large counts so that we can use, what did we use to find our probabilities last unit? We already found standard deviation. We used it in the, what did we use? Yeah, what CDF? Normal. Well, why could we use normal? Because we made sure it was normal with large counts. So what does large counts do? Assumes normality. This is important because when can we use Z? When we standardize and make it a normal curve. It has to be normal. If you don't check normal, you're going to get the entire problem wrong. You have to check it before you can use it. Got it? All right. So using table A or technology, find the critical value Z star. All right. So I'm going to show you technology. We've already done this before. Okay. When we draw this curve, we want it for 80%. How much is left? 20%. But I have split it on either side. So how much is left on either side? Is everybody okay with that part? Sure? Okay. You have to know this. If you don't do this, you can't use technology. You got it? So remember, to figure this out, we do inverse norm. Make sure you write everything down. It's going to ask you for the area, the mean, and the standard deviation. So in our calculator, second vars, inverse norm. What's our area we're looking for? What are we looking for? Here's why. We need this number right here. The way we do that is we get rid of, this is what we want, these numbers. Okay, so what's our area we're going to be? 0.1. Okay, so don't forget that. Don't forget that. And then since this is normal and we have z's, what's our mean and our standard deviation? 0 and 1. Okay, again, because we standardize it or we're using the standard normal curve. So area 0.1, don't care about left, right, center. It's not important. And what do we get? Okay, so the reason we have left in there is because this one is negative 1.28. It's on the left side. If we did right, what do you think we're going to get? Okay, so inverse norm, right, and then it's enough, paste it in there, and we get the positive. So there's nothing any difference. It doesn't matter which one you use. You know that it's going to be either positive or negative. So on the left, it's going to give you the negative. Positive, it's going to give you the right.
What does center give you?
Sorry.
Just for non-information.
No, you're fine. I don't mind you asking. 0.1. What does it give you? That's weird, isn't it? Are we ever going to use center? No. It gives you the 1% in the middle of the curve. So it's giving you like these little tiny right at the mean. Okay, it's 1% on either side of the mean. So we want the left and the right tail, and it doesn't matter which one you choose, left or right. Okay, good question. All right, so there's our negative 1.28 or our 1.28. So how do we do it if we're doing it in our calculator, okay? Or even if we're doing it by hand. So Z equals, remember it's our mean minus what we want over our standard deviation or whatever we're at. So we wanted 80%. So we're doing 1 minus 80%. And then our standard deviation or in our calculator is going to be 2. We're going to talk about this. I don't want to show you by hand just now. I want to show you this. So we're going to get to table A. Okay. I don't want to do it today. I want you to just do it in calculator, and then tomorrow we'll talk table A. Is that fair enough? All right, make sure that you have those tables, period. I'm gonna do a couple more with you just to make sure that you know how to do it. Let's do 95% in our calculator. So that would mean we're looking for 95% here. What do we have left on either side? 2.5, which translates into an area of 0.025. Are you guys okay with that? So we would do inverse norm what's our area going to be? And then we're going to keep our mean and our standard deviation. We do not want center. You can do left or right. It does not matter. So it's not really 2 and -2, is it? Remember 95%? We were guessing that our critical value was 2. You guys see that? The more precise is I told you it would be 1.96 a couple days ago yesterday. Whenever I told you it was going to be 1.96. So 95% confidence is going to be a critical value of 1.96. So what if I said 70? What would the other side be? 15. So 0.15 would be your area. Stop doing that. 0 and 1 on the left, and we get -1.04 or 1.04. And again, these are critical values. So now when it asks you to find the critical value for a C level of 80, you can find it. All right, flip it over. Once we find the critical value Z star, our confidence interval for the population proportion P is, okay, so remember we had statistic plus or minus critical value times the standard deviation. We're changing our formula. This is the formula that you'll see on your formula sheet. Our statistic is P hat. Our critical value is our Z star. And then to find our standard deviation of a proportion, P 1 minus P over N under the square root. And again, because we're talking about the sample proportion, it's going to be P hat. Yes, yes. That is the same formula from last time. We're just changing it to P hat because we're talking about the sample proportion rather than the population proportion. Okay. Notice that we replaced the standard deviation of P hat with the formula for its standard error. The resulting interval is sometimes called a one sample Z interval. It's the same title as the box below it for a population proportion. That box is the same exact thing that we just wrote. When conditions are met, C % confidence interval for the unknown proportion P is P hat plus or minus Z star square root P hat 1 minus P hat over N, where Z star is the critical value for the standard normal curve with C % of its area between negative Z star and Z star. So this bottom part is what we just did over there. The negative Z star and the Z star are the two vertical lines that we made. That was it. Now we can get the desired confidence interval for Mr. B's class. So calculate and interpret a 90% confidence interval for P. So this is the first time that we'll be doing that. And then we're gonna talk about his claim. We're gonna do the check your understanding and then we'll stop. There's actually only one more page to do. So I think you'll be okay in your homework, okay, to do whatever. If you're on Zoom, obviously your homework is not due till you need it to be due. You got what I'm saying? Yes. If you have questions on it, you can turn it in tomorrow after you ask those questions on Zoom. Our Zoom should not be very long tomorrow, okay? And then you'll have a second assignment. So I would try to get as much possible done now, like as soon as we finish, rather than waiting and doing both assignments tomorrow, okay? So this page in the back, and I'll stop. All right, so remember our formula is P hat plus or minus Z star times the square root P hat 1 minus P hat over N. I would suggest that you write this formula every time. Define what you have. So when we get into the ones where it's like state plan do concludes, like those, you want to make sure that you define all your variables, okay? So I'm going to do that same thing right here. P hat is our proportion. We already did this earlier. He had 107 red beads out of 251, which was 0.426. We need to find Z star. So we're doing a 90% confidence. So what's left over? On either side is 0.05. So we're going to do inverse norm. And our area is 0.05. Our mean is 0. And our standard deviation is 1. I would always use, oh, we got 6.4. Sorry, 6.5 is from the table. And again, I'll show you guys how to do that. 1.64. And then we're going to plug it in. What was P hat? Plus or minus, our Z star was 1.64 times the square root 0.426, 1 minus 0.426 over our N was 251 beads. All right. I always do the minus first because that's the one that's going to be the lower one. So I'm going to type it in and then I just resubmit it in there and I'll show you what I'm talking about. Minus 1.64. I do parentheses. I do the square root and then under the square root, I put a fraction. Okay, makes it a little bit easier. 0.426, 1 minus 0.426 over 251. Get all the way out and close those parentheses. And then when you hit enter, you get 0.375. And I just do 3 decimal places. You can go back up and highlight like you guys do. That's fine. I just hit second enter, but then go back and change this to a plus. There is an easier way to do this, but I'm not teaching you yet. So don't give me no homework with some easier way on it. Got it? Okay. 0.477. That's your interval. So that's all you do. Part B says he claims that exactly half. What is half? 50% of the beads in the container are red. Use your result from part A to comment on this claim. Look at this interval. What's the problem? Perfect. Because interval doesn't contain. And remember, these are intervals of plausible values. Does not contain 0.5. That's exactly it. Good job. All right, so the check your understanding is a combination of everything we've done today. Checking conditions, finding the z-score, finding the interval, and then we got to interpret the interval. So we're going back to 8.1 where we interpret it. So this is the last thing that we're doing. All right, identify the parameter of interest. So we haven't done this in a little while. What's your parameter of interest? So alcohol abuse has been described by college presidents as the #1 problem on campus, and it's an important cause of death in young adults. Sorry, how common is it? A survey of 10,904 randomly selected U.S. college students collected information on drinking behavior and alcohol-related problems. The researchers defined frequent binge drinking as having 5 or more drinks in a row, 3 or more times in the past 2 weeks. According to this definition, 2,486 students were classified as frequent binge drinkers. So what is your parameter of interest? Is it a mean? Is it a standard deviation? Is it a proportion? What is it? It is. How do you know it's a proportion? Perfect. They'll tell you. I mean, they'll tell you if it's a mean. They had an average of, they had a mean of. We didn't see that. If it's standard deviation, they'll say it's a standard deviation of. Y'all got it? Or it varies, blah, blah, blah. All right. So it's the true proportion. And remember, a parameter talks about the population. So of all U.S. college students, who are classified as binge drinkers. That's #1. That's it. So that was early on 8.1. All right, check conditions for constructing a confidence interval. So what's the first condition I have to check? Do we know if it's random? It says what? Randomly selected, where's it at? Randomly selected U.S. college students. Good. We're going to check the 10% rule. So we're doing 10 times, what was our sample size? Do you think that there's more than 109,004 U.S. college students?
Yes.
Yes. Large counts. What were our successes? Which is greater than or equal to 10. What would our failures be? How would you find it? Okay, so 10,904 minus 2,486 gives us 8,418. And I just wanted to put that on your notes so you guys knew where that number came from. It wasn't a random something I wrote in there. So what does that tell us we can do? What's the 10% tell us we can do? We can do the standard deviation. What's large counts tell us we can do? Assume normality. Got it? All right. We learned something today. All right. Find the critical value for a 99% confidence interval. Show your method, then calculate the interval. Okay. So 99%. What do we have left over? 1%, but on either side would be 0.5%. Watch your zeros. 0.005. So we're going to do inverse norm. 0.005, 0, and 1. And again, I would make sure that you label what those are. And I'm going to go ahead and tell you that you get 2.575. And I would go ahead, even though on the last one I did 2 decimal places, I would go ahead and do 3 on your Z-stars. Okay. All right, so what do we need for our interval? What's the first thing we need?
Are you choosing the positive one? Because if you
Uh-huh.
say-
Because think about it, if you do plus negative 196 times blah, 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 or whatever, it's still gonna cancel itself out. So I just always use it so it's less confusing. Yep. All right, what's the beginning of our formula? P hat, right? So what's our proportion? Remember, it's what we want over the total. We wanted the binge drinkers, which was 2486, out of our sample size, which was 10,904. And that gives us 0.228. We have our Z star, so we don't have to worry about that. And then you may want to put that your N was 10,904 somewhere, just anywhere, label everything that you're going to use in your formula. So our formula is P hat plus or minus Z star times P hat 1 minus P hat over N. Your P hat is 0.228. Plus or minus your Z star is what you found up here. I'm going to label it 2.575. Square root 0.228. 1 minus 0.228 over your N, which was 10,904. I will go ahead and tell you that that is 0.218 to 0.238. Now we have to interpret it. Last thing, interpret it. How do we interpret a confidence interval? It's the same thing every time. We just replace it with the context of the problem. Why'd we use that 99%? That's what they told us. Okay, don't feel like I'm being stupid. Eventually you'll start doing 95 so much that you'll forget to change that. Okay, so remember to watch that confidence level. Confident that the what? What do we find?
Oh, the interval.
Uh-huh. What does that interval do? What's that verb? Captures. Captures what? The true. And why do we use proportion? Because that's what we were looking for. We weren't looking for the true mean. We weren't looking for the true standard deviation. We were looking for the true proportion because we used P. And then it's in context of the problem. The true proportion of what? Of all, because we're talking about the population. So you have to use the word all. U.S. college students. Just like we wrote in the beginning, who are classified as binge drinkers. Tomorrow you'll have one that putting it all together as the state plan do conclude. It's basically what you just did in 4 different steps. Okay, so don't stress about that. And then we just have 2 pages of notes, or a page and a half. So we're good. All right, I'm gonna stop sharing and stop recording.